presented by Caltech.
Hi everyone, thanks for coming. It's a great pleasure to be here. I'm Ravi. I work at JPL for the machine learning group. I've been working at JPL for the last 5 years, and I have also been collaborating strongly with Esong's group on some very challenging problems for JPL applications. I'm going to talk about one of them in today's talk. So let's get started. So the overall outline of my talk is the history and the future of autonomy in space exploration. I'm also going to talk about a case study in risk-aware path planning, more in particular retrospective imitation, which is one of our study, and I'm also going to talk about some ongoing research for rover navigation that uses retrospective imitation. Okay, a brief history of space autonomy. Started with Explorer 1, which is the first American satellite. Pioneer 4 was the first lunar mission that was successful. They were fully autonomous because they did not have any receivers on board. They just had transmitters directly connected to the sensors, and they were pretty much just flying sensors. Their mission was to take, Pioneer 4's mission was to take a photo of the moon. They had a timed mechanism for de-spin to control the spin of the satellites. And they were triggered, the photoelectric sensors were triggered by the light of the moon. So, and then in the 1960s came the digital computer revolution, and we had the Ranger 3 with limited Earth-based control. There were like sequence of instructions sent to Ranger 3. It had onboard memory and storage, and these sequence of commands were executed on board, but there was no autonomy on board. It was pretty much just everything, sequence of instructions sent from Earth. And then we have the rovers, M2020 Curiosity and M2020 rovers, pretty much supporting critical roles for autonomy. And the Voyager 2 in the 1970s, with a failure for the primary sensor, the onboard algorithm for autonomy saved the mission by switching to the secondary sensor or the receiver. Into the future, we have the M2020 mission, we have the Europa lander, and other missions requiring heavy autonomy-related problems with innovations in some of these machine learning problems that are very challenging. So I'm going to talk about some of them. Into the future, some of these rovers are dedicated to driving. What you have here is M2020 rover, which is expected to drive for 12 kilometers in 85 sols. Sol is a Martian day. We also have the conceptual sample fetch rover, which is expected to drive for 1 kilometer per sol, and then the water transporter, which is also a conceptual, which is expected to drive for 3,000 kilometers in 100 sols. As you can see, some of the future rovers, futuristic fetch rover and the water transporter, they are powered by solar. And M2020 is powered by radioisotope thermoelectric generator. So there's more leverage to have instruments on board. But for future fetch rovers, there's literally limited instruments on board, and there is greater demand for driving longer distance. right? So there is greater interest for autonomy for space exploration for the following reasons. We need enhanced productivity and safety. You want these drivers to drive longer distances for science returns, and you want them to also be aware of the potential dangers in the environment. There is severe communication bottleneck with some of these missions. For example, we have the M2020 or the Curiosity and Opportunity rovers, where for nearly 7 minutes we don't have any communication with these spacecrafts, and they have a sequence of instructions for landing on the surface of the moon, which is a very challenging task, and with very limited communication. Right, so there is also onboard processing rather than downlinking all the raw data. Right, so these are pretty much because of severe communication bottlenecks with these spacecrafts. There are other missions where you have to quickly complete some of these missions because they are very short-lived. For example, we have these missions for Europa, where the mission is expected to function for no more than 10 days due to radiation, and the Venus surface mission, which is expected to function for only a few hours due to extreme heat. So these are some of the reasons why there is like a renewed interest for space autonomy. Right, so most of these missions are for science, and improved autonomy can drastically improve the science returns that we can get from some of these missions. So I'm going to get into a case study, which is the risk-aware path planning, which is one of the critical applications for rover autonomy for JPL. So what is risk-aware path planning? So there are some guarantees that you want to get from some of these rover navigation algorithms, which is obstacle avoidance, and you would also want them to, with guarantees, stay away from the obstacles and not crash into them. So what do we mean by that? You want the behavior to be adaptive depending on the environment, right? So for example, on the left, you have a scenario where you have instructed the rover to take very low risk. So it goes around the obstacles. This is a simulated environment at JPL. Actually, this is a Martian Mars yard, which is pretty much simulated, I would say. These are, yeah. So on the left, you have a low-risk scenario where the rover is instructed to go around the obstacles because you want it to take low risk in the environment. And on the right, you have a high-risk scenario where you have instructed the rover to take as much risk as it likes because you're really aware of the environment, right? So how are these problems actually encoded? So given the set of obstacles that you have seen on the previous slide, we have polygonal obstacles. We abstract the environment into a set of polygonal obstacles, and we frame it as a stochastic optimization problem, wherein the objective could be minimum distance, or it could be the traversal time, and the constraints are effectively obstacle avoidance, how much battery power do you have, and also control related constraints, right? So this is a large scale stochastic optimization problem. It's stochastic because you have uncertainty in the location or the state vectors, right? So most of these problems in real world scenario are actually solved as a tree search branch and bound problem, wherein the branching factor is the variable selection. For our problem, in particular, the variables are effectively the side of the obstacles that you want to take. And the state is pretty much the partial tree that you have explored for our problem. This is a pretty standard conversion of a tree-based path planning algorithm into an optimization framework. The way it's actually solved in real world is you just throw a bunch of expert solvers that throw a lot of heuristics on solving some of these branch and bound algorithms. Right? They're not specialized to some of these problems in particular. So why is this hard? Because as you can see, with increasing number of obstacles, you can read the x-axis as the obstacles ranging from 10 obstacles to nearly 50. And on the y-axis, I have the running time for some of our simulations. It grows from a minute of running time for 10 obstacles to more than an hour for roughly around 50 obstacles. Right? So we can't afford to do just path planning on these rovers for nearly an hour. Yeah, so because these are computationally hard, we want to be able to solve these more efficiently. So here is a real world example, I would say. This is a picture from the Spirit rover on Sol 108. Sol is the Martian day. We had this naive tree search based algorithm, and in this current scenario, tried to solve path planning for nearly, not even risk, like a naive path planning algorithm for nearly 2 hours. It kind of failed and had to call back home for help. And so that's how hard these problems are, and so any advancement in some of these algorithms will have a huge impact on the science returns that we can get from these missions. So I'm going to talk about some of the work that I've been working on in collaboration with Isong's group. It's called Learning to Search. So so as you can see, some of these problems can be solved very efficiently on small scale problems. Like if you have say 10 obstacles, it can effectively be solved very quickly. So our idea here is to use demonstrations from small scale examples and iteratively improve our performance to scale up to large scale problems and solve them effectively. Right? So here what we are given is a family of distributions of search problems and solved instances on the smallest or the easiest instances, which I would say in some of our experiments we have it ranging from 8 to 10 obstacles. Our goal is to build on existing imitation learning algorithms to be able to scale up to hard instances of path planning algorithms. Right, so here is a high-level simulation of our algorithm. So imagine you have trained a policy using imitation learning on small-scale instance, and now the algorithm is actually given a large-scale instance. We roll out the policy on the branch and bound algorithm to find a solution, and iteratively improve the performance of the policy using retrospective feedback. By that, what I mean is all the nodes that are marked in red are supposed to be better nodes for exploration to find a good solution compared to the other nodes. So we prepare our data by featurizing some of these nodes and iteratively improving on the performance of the policies. Right? So now the data pretty much says all these nodes and their features are better to explore than the ones that are not colored. Right, now that's the improved policy, pi2, and we are able to reduce the search space and improve the time effectively. Now we do this iteratively to improve the performance of the oracle. Right, so pretty much like we deploy a policy using imitation learning algorithms. We then use the retrospective feedback from the branch and bound space, and then we retrain some of these policies. It's a standard procedure in imitation learning, but the trick here is we don't have an expert feedback here. We are able to solve some of the large-scale instances with its own feedback. It's trying to improve its own performance by exploring the hard instances on its own. So this also belongs to a class of semi-supervised algorithms, where the supervision is only from the easy instances. For some of our experiments, we used a neural network as a policy class. To be more specific, we were looking at ranking networks, and so here is a more empirical results. On the y-axis, you have we have the number of binary variables which is equivalent to saying the hardness of the problem, and on the y-axis we have the quality of the solution. Skip, which is the brown one, is the best available open source solver for some of these branch and bound algorithms. The one in green, Garobi, is the commercial solver. There's billions of dollars spent on developing some of the heuristics for tree search algorithms, or branch and bound in particular. And in blue is our approach. We are able to get more than 50% improvement in the quality of the solution, and in terms of runtime, some of these algorithms, like if you see there's 560 variables in the largest scale instance, which takes roughly about, like, on an average, like 15 to 20 minutes, we're able to solve it in less than a minute. So there's a huge gain in terms of runtime, and there's significant improvement in the quality of the solution as well. So what are we gaining here? The demonstrations are pretty much only from the easy instances. We iteratively improve and imitate high quality solutions and large scale problems using great function approximators like neural networks. During test time, you can converge to high quality solutions on hard instances. Then and the framework is also general enough that we can actually apply some of these frameworks for scheduling algorithm, traveling salesman problem, most of the algorithms which can be framed as a branch and bound algorithm. So this is actually ongoing work, where we are trying to apply some of our learnings from retrospective imitation to rover navigation. And this project just got funded. I'm really excited to be working on it right now. So what is the project about? It's called Autonav. Autonav is an existing algorithm and it stands for autonomous navigation. On a high level, if you're just doing manual path planning, some of these rovers are limited to the line of sight. You have just 50 meters of line of vision. Your bottleneck is the uplink and downlink time. Each uplink and downlink is pretty much done once over a sol. And so Autonav's objective is actually to extend the autonomous driving distance. Right, so Autonav is an existing framework with a naive tree search, which I'll talk about in the next slide. Autonav, the existing framework, actually doubles or triples the driving distance from the blind drive. Our objective in the ongoing work is to increase that further by doing effective search on the tree-based algorithm. What do I mean by that? So the existing framework, for the existing framework, we have a naive tree search where you choose a path from a depth 4 tree. As you can see, it's very similar to the branch and bound space that I showed you guys earlier. This is in terms of computational complexity, it quickly grows exponential. In terms of the branching factor, which is limited to 3 because of the complexity, and the depth is also limited to 4 at this time for Autonav and the existing framework. So our work is actually focusing on leveraging some of the algorithms that we developed in retrospective imitation to enable autonomous driving on a complex terrain for longer driving distances. That's the end of my talk. Yeah, it's been a great pleasure collaborating with some of my JPL folks and the Caltech folks. Big shout out for Jalan, who is sitting back there. He's been collaborating with me for a while on similar problems. Questions? Yeah, so it does give you an optimal solution, but there are no guarantees on the runtime for the solvers, right? So there are instances where we pretty much spend half a day trying to find an optimal solution, right? Our objective here is to find a feasible solution that satisfies the constraint, and in the limited time that we have, find a really good solution. That's the overall objective. Yeah. So it's hard to study the optimality gap, but I guess there is quite a bit of empirical study on how learning helps in finding good solution. And so as soon as you talk about good solutions, there is only the question of duality gap because you don't know the optimal solution. So, okay.
What is success?
At least for now, we are looking at 3 times the Autonav distance. So, is it doubling the Autonav, I would say. 3 times the manual driving distance. At the same time, there's also some gain on computational the computing power.
How far does Autonav travel?
So that's roughly around 150 meters.
150 meters a day.
Yes.
Okay.
Yes.
So if this project is successful,
We're looking at something around 300.
300 meters.
Yeah.
That's solar.
Yeah.
And do you need a GPU for this?
No, not really. But what we are definitely looking at is a low resolution height map around the rover towards the goal. Yeah.
Does this need more compute than Autonav currently uses on the rovers?
By this you mean?
I assume that these rovers are using all the power all the time. Like
Yeah.
they're super resource limited with like tiny computers and
It's
radiation hardened. So like if this system, I'm being my own critic for my project, but
sure.
if these systems require more compute, is that an issue?
Definitely is an issue for M2020 because some of the processors on M2020 is equivalent to 90s Mac computers, right? However, there's also a helicopter flying with M2020, which has a processor that is as good as the one which is in your mobile phone. So it's getting better. But that's also a challenge, which is also why we need better search algorithms on board. No, not so much. Sure. So that's also, yes, you're right, because if you have a tree search, you're using the existing structure, and there's also some work that we use for combining branch and bound and tree search algorithms, which does improve the exploration side of the algorithm. However, I think the tree search algorithms also will require you to have heuristics on board, right? So if you have A star, you still have to decide on which nodes to explore, right? We are using learning to decide which node to explore, right? Some of those heuristics are replaced for A star. Some of those heuristics are replaced by the machine learning algorithms which know the environment better.